Hi guys, so today we will be starting with a new question number 12 from group B, which is to write a Python program to store names and mobile numbers of your friend in sorted order on names. Search your friend from list using binary search, recursive and non-recursive. Insert a friend if not present in the phone book. So basically we have to search that person if he is not present. So first let's just copy this thing and move on to our text editor. So let's just paste this thing here and let's just remove this and let's just save and then comment. And after that, let's just see what is this question actually asking. Let's just improve this a bit and head on to our board to see basically what this question asks. So here, basically they are asking that we have to search for an element. So in the last session, we saw how we can search using linear search and sentinel search. But here we have to store the name and the mobile number. So we have to store basically these two things, and then we have to search using first of all sort these values depending on the name, and then search whether that person is present or not. So basically we have to create a phone book. So the context which we see in our mobile, basically we have to perform that thing. So let's just see how we can do this. So first of all, it depends how we store the values. So we can store these values anyhow. So there are basically two things. We can use a tuple or a list depending on our case, and then the second one is using class. So let's just basically say this using tuples and list, so that if anybody doesn't know anything about classes and object-oriented programming, they too can continue. At last, if time persists, let's just see how this will be implemented using the class. So yeah, now we have, and let's say, a tuple. So we have a tuple of name and mobile number. So this will be stored like this. So name 1, mobile number 1, name 2, mobile number 2, and etc. So instead of directly jumping on this values, what we will see is we have asked to implement binary search. So instead of directly implementing on that complex data, we will use a simpler data. We'll learn how the binary search works and then just implement that. So here, let's just take an example. So the same example of a list with some integers. So integers would be easy to understand, and then we can move to the alphabets. So let's just take 35, 46, 53, 97, 110 to 20, and yeah, this should be the list. So basically now here you can see this list is in sorted order. Basically sorting means arranged in some specific sense. So either ascending or descending. So either both of the one way means every value is either greater than the previous value or either less than the previous value. So any of the two ways can happen. We would be mostly considering ascending values. So this would be greater. So the last element would be the greatest element and the first element would be the smallest. So this thing is called as the creation, or this fashion is called as the sorted order, and we use sorting algorithms to do this. So now this would be covered in future lectures how the sorting works, but for now let's just understand that we have given a sorted list. So what we have to do is basically, or instead of just taking this complex number, what we can do is let's just take very simple numbers. So 1, 2, 3, 4, 5, 6, 7, 8. So this would be our basic array. So what we have to basically do is here we will be basically starting. So let's just first assume, let's just first consider an example. So just assume that I give you an word and you have to search that in a dictionary. So let's just say I give you for searching for algorithms itself. So algorithms will lie at the first part of the dictionary because A lies first, then B, C, D, E, F and Z. So basically if I give any word, so let's say algorithms, you will check the first letter and depending on that you will search in the dictionary. So if this is a long dictionary, I have arranged this linearly, so you would search somewhere here. Okay, similarly if I give some complex value, so sorry, instead of complex, any other word such as instrument. So if I give you an word instrument, it is somewhere between. So it lies somewhere between. You will just open the center page of the dictionary, randomly you will open, and then if let's assume you got the center as M, so any value starting with melody. So let's assume this is a dictionary and you got a word called as melody here in the first page. So now I comes before M. So in the alphabetical order, I comes before M. So I know that the instrument would always appear before M. So it would be somewhere here in this shaded portion. So it would be somewhere here near about. You can approximately guess this. So here you are guaranteed that the values will not reside. So it will not be here in the orange colored portion. You are guaranteed. Why? Because this dictionary is arranged in sorted order or alphabetical order and always I comes before M. So it will lie somewhere here in the blue part. So it will not also exist in this M part because here it is M. So like this we can directly reduce the half of the search space. So what is the search space? Basically the whole thing on which we are searching is called as the search space. And if we are removing these all things, so we are removing the means reducing the search space. So yeah, this is the basic working of how the binary search works. So here, just a second, let me just remove this example. So here we have to perform something similar. So here what I am doing is basically I know this list is in sorted order. So what I can do is I can find the mid of this list. So here it starts with 0, 1, 2, 3, 4, 5, 6, 7. I'll be working on indexes. So I can consider this last index and the first index. So basically these are the values. So it is 7. So if I check the midpoint, it would be 7 by 2, which is 3.5. And in the list, we can't take any value. So either you can take the seal or either you can take the floor. So I will just do integer division. So I will take 3.5. So it will return me 3.5. Sorry, it will return me 3 depending on the integer division. So now I received 3. I am searching for this. So let's just say key. The key value which we are searching is uh, let's just take 7. Okay, so what would happen is now I know this is the middle element. Now I can check whether the 7 exists left side or right side. So where does the 7 exist? So here I know this is 4. So if it is less than my key, then this all part won't be helpful because my key is greater than this. So it will always be present in the right half. So I can then search in this part. Similarly, if I say that we are searching for something like 2, then I know that it will always be present in the left half. Why? Because uh, greater than 4 elements is present in the right half and 2 is always less than. So depending on the condition, we can move this thing. So let's just now consider for 7 itself and then check for another value. So here now we are checking for 7. So what has now become? So first of all, I was searching from 0 to 7, all the elements. Now I know I have to only search between 4 to 7. So what I can do is this is my starting point, this is my ending point. I can find out the mid element. So basically 4 plus 7, which is 11, 11 by 2, which gives me 5. So integer division, which gives me 5. So I can select this and I got 6. So is 6 less than or greater than? So basically it is less than. So I know left part is not that useful for me. So I will again reduce this space, and now I am between 6 and 7. So I will again compute. So 6 plus 7 gives me 13. 13 by 2 gives me 6. So now my middle point is 6. So here is the midpoint. So I will check whether the key value is same or not. So here I can see 7 matches the key value. So I can return this index, which is the 6. If this was not the case, if in some hypothetical condition, if this comes, somehow 7 we got as the midpoint, then what would we do is we will ignore this and we will go to this point, because the right part from the middle element we don't need, because it is not our case. It is the value will not be there. Then we will again come, we have got only one value, 6 and 6. So 6 plus 6 divided by 2 would give me 6. I will again check if this element exists or not, and yeah, it exists. So this was the basic case how this should work. So here now I basically can deduce some formulas. So first of all, I have to take lower plus higher divided by 2, in Python terms divided by 2, and this would be my mid value. Then I have to check whether the mid value is same as the key value or not. So mid of, let's just take list as L, or not L, let's just take A array equal to key. If this is the case, then we have to return the mid. Okay, so this is somehow this I know, because basically if it exists here in the mid position, then we will return that. But if not, then what we have to do is, if A of mid means the middle element is less than the key, means it will always exist in the right part. Why? Because here we just saw, if we are searching for 7 and this key value which was 4 is less than 7, then our values will be present in the right part. So what I have to do is, if I assume this is the lowermost lower index and this is the higher index, I have to just update this lower index to this thing. If I assume I have two indexes, L and H, lower and higher, I have to basically update this higher to mid plus 1. So what I can do is here, so L is equal to mid plus 1. Similarly, if A of mid is greater than the key, so my key is less than, means it will reside in the left part. So what I can do is I can reduce the H now. So H is equal to mid minus 1, and we have to go on like this. So we have to stop somewhere. So here, so yeah, let's just take some another example and see what would be the stopping condition. So let me just remove this all, and yeah, so now let's just say I have the again list 1 2 3 4 5 6 7 8, and I'm searching for something like key is equal to 10. Okay, it is not present. So when we have to stop, we have to basically see when we have to stop. Or let's just take or the list maybe anyhow. So let's just remove this 5 and let's just search for 5. Okay, so this case would help us a lot instead of this 10. So we will see that. So let's just take keys, just a second, key is equal to 5. So what I have to do is I have to basically search. So this is 0th element, first, second, third. Let me just change my color. So 0 1 2 3 4 5 6. So this is my list. Sorry, this is my indexes. So lower is equal to 0, higher is equal to 6. So higher is equal to 6. So what will I do is, now I will calculate the mid value. So mid is equal to L plus H, 0 plus 6, which is 6, divided by 2, which I get is 3. So first mid is 3. So what I will do is I will check whether key is same or not. 5 and 4, no, not same. Key is less than 5, yes. So what I have to do is I have to update the L. So I updated the L. So now L is here pointing at the mid plus 1, means 3 plus 1 4. Now what I have to do is again calculate 4 plus 6 10. 10 divided by 2 is 5. So now the midpoint is this. So mid is 5, and we will check 5 and 7 same. No. So 5 is less than 7. Yes. So let's just modify this to h minus mid minus 1, which gives me 5 minus 1, which is 4. So now I will check. So again L plus h, which is 4 plus 4. 4 plus 4 divided by 2 gives me 4. Now I will check 6 is same or not. No, it is not same. Then whether 6 is greater than or less than. So 6 is greater than. So what I have to do is I have to reduce h equal to h minus mid minus 1. So basically, sorry, h is equal to mid minus 1. And in this case, mid is 4 and I have gone to 3. So is this correct that lower position is greater than h? So is this condition correct? So basically, or instead of saying this, this is the logical way, or whenever, here by this conclusion we can say whenever h is less than L or length is greater than h, if somehow this condition happens, then we have to stop. So basically this is the terminating condition. Why? Because higher value, higher index can never be less than the lower index, because if we assume some range 0 to 1 and we do some operations and we are saying that this is our valid range, and new range would be minus 1 to 0. So we were only let's just say we are only discussing about this number line. Basically, if I start somewhere here, so if I start somewhere here, this is my lower point and this is my higher point. Can I say somehow that if here is 3, this is 4, 5, 6 and 7. So somehow h came here. So can I say 3 is greater than 4? Because h is higher, L is lower. So can I say this? No, this condition becomes false. So that's the case. Therefore, this condition comes that length should be always smaller. So yeah, so we found the terminating condition 2. We have n pseudocode 2. So this is n pseudocode, basic pseudocode. Let me just reduce it a bit. So this is the pseudocode and we have to implement. So yeah, basically this will be implemented inside the loop because we are doing the same thing again and again. And when this loop will stop? At this condition. So L should be always less than H. So yeah, let's just go back to our text editor and let's just do this thing. So now we have a basic idea. So yeah, for loop, as we talked about the loop, we will first use non-recursive method. So let's just define a function. So define binary search and let's just take nr. It's non-recursive, and this will take a list as usual, and then instead of list, let's just take a, and this should take a key because the element which you have to search. Then basically at start we will require to index L and H. L would be 0 because list array starts from 0, and H would be length of list minus 1 because array starts from 0. Then while L is less than H, while this condition is true, what we have to do is we have to calculate the mid. So mid equal to L plus H floor division 2 because we will get an integer value. Then after finding mid, we have to check if a of mid is equal to the key value or not. Basically I am checking that current index which I am at is equal to the key value or not. So if it is equal, then I will return mid. Else if what we can do is if a of mid is less than the key, means the key is present at the right part. So L is equal to mid plus 1. Yeah, then the last condition is else, means here we know a of mid is greater than key. So what I can say is it is key is residing in the left part, or we can also put this condition too for more clear understanding. So a of mid is greater than the key, then what we will do is h equal to mid minus 1. Yeah, so this is the basic case. Then what we will do is this will continue, and if nothing is returned from here, means it is not present in the list, because we did all the calculations but we not found that element. Then what we'll do is, as usual, we will return minus 1. So return minus 1, so that this says that there is no element present. So let's just create a list. So here the question is regarding the mobile number and name, but first let's just implement the simple binary search and then see how we can do this. So yeah, what we can do here is, let's just create a simple list. So let's just create an A list or L list. It should have some numbers, but this should be sorted. 145, 67, 89. Just a second. 1, 4, 5, 8, 9, 10, 16, 45, 89. So this would be our list. We have to perform binary search. So let's just print binary search non-recursive. Why it is non-recursive? We are not using recursion. So what is recursion? Recursion is basically function calling itself. So then what we have to do is we have to pass a list and we have to pass a key. Let's just say key is 89 and let's just execute this. So here int has no type length. Okay, L, we don't require L. Here it should be A. So here 89 is not present. Okay, there is something here. So we are providing this, and yeah, med is calculated every time L plus H by 2. Okay, maybe this L is updated. So instead of this L, let's just take array. And here let's just put, maybe this won't be an issue, but let's just check. So 89 is not getting printed. Why? So what will we do here is L plus H by 2, return mid, and L is equal to mid plus 1. So let's just use dry run and check why isn't this working. So mid is calculated. Yeah, everything looks fine. So let's just go back to our thing and let's just recalculate this. So yeah, so I just selected this. Just a second, I'll just increase the size. It isn't that visible. Just take Excel, just increase. Yeah, so this should be now visible. So this is our basic list. Let me make this a bit smaller, and let's just come back. So here let's just give indexes 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, at first 8 by 2 mid will be calculated as 8 by 2, 4. So 4 we are checking is 89 greater than, so mid is less than. So what would happen, this would be rejected and L would be here. First L was here, H was here. So length of this minus 1. Yeah, so after that what happened, 5 plus 8 which gives us 13. 13 divided by 2 gives me 6. So now this is the middle element, checking it should be greater, removing this L. So here 7 plus 8, so 15. 15 divided by 2, 15 divided by 2 gives me 7. We check for this, so we have to remove this, and L is this thing, so mid plus 1. Okay, so now 8 by 8 gives me this thing, so this should work fine. 8 by 8 gives me, sorry, 8 plus 8, 16. 16 divided by 2 gives me 8, and I have to check for 8, and this should return. So let's just see what issue has occurred. in our side. So to debug, what I will do is I will print out this thing. I'll print out mid in every case. So let's just print the mid and also print the L and H. So first value is L, then H, then mid. So let's just print. So here, okay. So here, as we saw in this thing here, as we saw, L and H can be at the same position. So it's not compulsory that L should be always less than. It can also be equal to. So it shouldn't be greater than only. So yeah, this was the case. L can be L would be less than or can be equal to the H. So they may be pointing at the same position and that may be the value. So that may happen. So yeah, you have to just change here, add an equal to and execute. So let's just remove this, comment out this print, and now we can see 8 is getting printed since it is present. Similarly, let's just print 8, third position, okay, fine, 10, fifth position, and let's just say 1, okay, 0th position. So now everything works fine. Let's just put some other value, 78. So -1 means it is not present. So basically like this we can search. So yeah, this was the non-recursive method. So let's just modify this to hold this for this given question. We'll just modify this function so that we can use this binary search on this names and mobile of number list. So instead of storing each individual value, what we have to do is we have to input some name and this thing. So let's just give simple names such as A. It would be a string A, and then the number as number can be anything. Let's just take 10, and let me just copy this a bit and paste this. So instead of A, this should be B. Let's just say C. This should be D. This should be I. Should be S. Let's just take some more values. After S, let's just take W and Z. The number also, let's just take 79. So here, as they have said, write a Python program to store names and mobile numbers of your friend in sorted order on names. Basically, we have to save this in sorted order, and it is depending on the names, not by the phone numbers. So phone numbers can be anything. So it can be anything. So let me just create something, and so this should be the values. And now we have to implement the binary search. So what will happen now? Instead of getting a single value at A of mid, we will get a tuple of 2 values. So basically, we have to check whether this thing is means we have to then check on the string itself. So string is less than or not, or greater than or not. So key will be string, and here A of mid would return me some values. So I have to only take the first value, which is the 0th value. Okay. So as I know, I have to only take the 0th value, the first value, which is the name, as we are searching from the name. So yeah, we are searching from the name, and key would be here. It would be something, let's say D, because we are searching by the name and the person's name is D. So let's just try this. So here we can see 0th index, first index, and second index. So let's just also copy this thing and save this index somewhere. So index equal to this thing, and then what I will do is I will print this index at first and then also print the value. So a array of index, so that I get whether I'm getting the correct value or not. So here we can see 2D89. Similarly, why this is happening? Because a string is automatically compared and they are compared according to alphabetical order, so we don't have to do a big change. Because if there are some another languages where string comparison is not supported, then we have to individually check each element and ASCII value, or you can, yeah, basically considering the ASCII value you can compute. But for now, this would be okay for you. So yeah, this is how we can use this binary search using non-recursive method. Similarly, let's just see how we can do this using recursive method. So let's just come back here again, just remove this, and we now basically know all the basic conditions of the binary search. Now what we have to do is we have to create a function such that it calls itself and terminates somewhere, because this is the recursion. Recursion means a function calling itself. So let me just remove this. Let me just go back a bit, and here. So as we started, so yeah, let's just remove some things. So I need the index. Yeah. So here, as I know, I started with 8 by 2, which was 4, and I came here, I searched for something, and I searched for the value, and if it was present, I was going ahead. If it was not, then doing something. And after that, after discarding this all values, what I was doing is I was again performing the same thing. I was again performing binary search on this list. If I assume I had a single list of 0, 1, 2, 3 with this thing. So if I just remove this, if I just consider I had some list as this, so I was calculating 3 by 2, which gave me 1. So it was here. Similarly, 5 plus 8, which is 13. 13 divided by 2 was 6. So basically, I was coming to the same location. So basically, what I can see here is I am basically doing the same calculation, calculating the same middle element, then again doing the same thing. So instead of doing this, means instead of again and again performing the same thing, what I can do is I can put this in a simple function and call it recursively. So what my function should do is, so my function should first of all compute the middle element. Okay, that's the first case, depending on the lower and higher index, which may change. At first it was 0 and 8, then it was 5 and 8, then it may change to 6 and 7 and 8. So it may change. So this isn't static. So what we have to do, we have to pass this somehow in the functions. So maybe we could make this as arguments or parameters. So we can make this as arguments, and this will be passed. So basically these two will be added to our function. So yeah, list will be the same, list will be passed, key will be passed, plus these two elements will be passed, because these are changing elements, and in recursion the changing elements are kept in the arguments, because we can't perform anything using, means we can't use any dynamic value inside a function without referencing it. So what I have to do is I have to basically calculate middle element using this lower and higher values. Then I have to check whether it is, if I got the value, then return, else if I don't get. So what I have to do is I have to basically reduce the else value. So L would be M mid plus 1, or what may happen is higher value will be modified. So any of these two may happen, and again call the same function, again call the same function. So this is the basic thing. And up to how many times I have to go, so I have to do this again and again until the condition was L should be greater than, sorry, until L is less than equal to H. Up till L is less than equal to H, up till that time I have to do this thing. So yeah, basic idea would be cleared. So let's just shift and code this a bit. So let me copy this same function, or let's just develop this from scratch. So define binary search, and it would be R, because we are using recursion. Then what we would lead a list, we can call this A array, then a key, and then we also said we need L and H. the lower and higher value. So then what would happen is, basically first of all I have to calculate mid equal to, so before calculating mid I have to basically calculate whether lower means I've gotten valid sequence of the list or not, means lower is higher less than higher or not, means L is less than H or not. So if L is less than equal to H, then only continue, else return -1. So return -1s. Why? Because if L is less than H and till now we didn't find the element, means element is not present. So then the mid value would be L plus H by 2. So integer division basically, because we don't need float values. After calculating mid, if A of mid is equal to the value, so is equal to the key, then we will return mid. Yeah, so we can return mid. Else what we have to do is, just separate this a bit. Else what we have to do is, this should be separate. So else I have to basically do, what I have to do is, yeah, if A is, let's just copy this same thing. So here, yeah, and what we have to do is basically L is -1. So then again call the same function, which is here indentation issues. This is not an issue, but formatting is wrong. So then what I have to return is, so basically I have to call binary search recursive. So binary search recursive, and here would be A as it is, key as it is, L would be modified, as we can see we have modified here, and then H as it is. Similarly I can copy the same thing here, and we have to return this value because we have to then pass this to next thing. So this should be the basic working of the recursive function. So let's just check whether this works or not. So yeah, we would, here the A of mid of 0 it should be, because we are directly checking on strings here. Now we are not working on mid, here we are not working on the integer values, so this would be required. Let's just see whether it works or not. Yes, it works correctly. So let's just put a value which is not present. So instead of D, let's just put E. Okay. So yeah, it is returning. So let's see why is it returning Z. Basically if I'm checking for E, what is happening, so it should return -1. Yeah, and let's just check for B. So still it is returning me this value. So yeah, let's just see. Okay, index is basically -1, and in Python we can use -1 index to access the last element. Basically this shouldn't work in any other thing, and this is because of this means Python supporting the negative indexes. That's why we are getting this printed, else it would throw an error that index doesn't exist in C++ or Java. Yeah, so this is the basic thing how this recursion works. So this is how the recursion works, and the we did the same thing on the list 2 with the names and phone number. So here now you can also put names basically. So let's just put AA, and I will here put, so let's just work on smaller values only, and AA, uh, and here AD. So here if we are checking for A, you can see this should also work. At first, okay, let me just see. Yeah, here I have modified this to A, but here as I've kept A to A, maybe what I can do is I can, let me just copy the same thing and I will just use it there. I'll use a single list and I will do the computation depending on that only. So after printing this using recursive, I will use non-recursive. So let's just see. Here nothing is provided. So A, yeah. So here you can see both AS are provided and I'm getting 0. So I can also provide D, and here also D, and both should work fine. I'm getting the AD as correct, and this works for this elements too. So if every element was a 2-digit element, so AI, AS, AW, AZ, then also it works fine. So here, as you can see, why? Because these are in sorted order. So basically Python considers AA as its, if we are comparing AD and AA, first element is same, we neglect it, we consider the second letter. So between A and D, A is less, so we basically do that thing. So therefore it works fine. So this was the basic thing, how we can create a program to find a person from the phone book recursively or non-recursively. So here, if we got this element, so here as we saw, as in the question, insert a friend if it is not present. So what we have to do, if he is not present, then what we have to do is, so let's just directly do here, if he is not present, then we have to add him. So let's just use a dot append, and we will add the key value. So we have to create a tuple, key value, sorry, not the a, key, and the mobile number. Let's just take some random value, we'll assign it for, or let's just take -1, since we don't know the mobile number, because we have to just set, we have just asked to add that element, so, sorry, add that person. Similarly here also, instead of returning -1, we can add that element, and we can return the a of length of -1. So length of a -1, because we will be adding it to the last position. Similarly, let's just do the same thing here also, return the a of, sorry, length of a -1, and this should work fine. So let's just see, if we are giving, let's just say z, let's just check. So here I am getting 7, it is added at the last element, last index. Let's just also print the array that you could get, and sorry, so here you can see at last it got added automatically. So like this we can add, and yeah, this is how we can do this thing. So yeah, this was all for this session. Here we saw how we can use recursive binary search and non-recursive.